Alright, so we're going to move on here to our next unit, which is going to be on waves and oscillations. So to begin this unit, we're just going to go over the basic definition of a wave. And so a wave is just a moving oscillation. Alright, so anything that's moving through the air. An oscillation is just something that goes back and forth. If we set that in motion, all of a sudden we have a wave. A few important things to know about waves. Number one, waves are capable of carrying energy from one location to another. That is one characteristic of all waves. This can be in many different forms, whether it's a water wave, a light wave, a sound wave. All of them are carrying energy from one location to another. And some of the biggest examples we're going to talk about, although this is not the only ones, we will talk some about water waves. We'll talk some about light and sound. We'll look at waves moving along strings. There's going to be lots of different types that we look at here. Alright, so let's go through a few basic definitions here. You do see the classic shape of a wave, and again, on the end here we have this mass on a spring that would be oscillating up and down. All we have to do is put that mass in motion, and those oscillations turn into the classic shape of a wave that we see, which would be a sine or a cosine curve as well, for those of you that are doing that in math class now. So we're going to go through a few definitions about waves. So I'll start with our first one, and that is equilibrium. And equilibrium is basically the center of the wave, or if you think about an ocean wave, if the wave had not yet moved through the water, where would the water level be? Okay, when a wave moves through, the water either rises above or below that point, but the equilibrium is just that middle point, that point if the oscillation or wave had not moved through it. Amplitude is going to be defined as the maximum displacement from equilibrium. So we see amplitude shown here on our diagram. It is important to note that it's always measured from that equilibrium position to a minimum, which is known as a trough, or from that equilibrium position to a maximum, which is more commonly known as a crest. Okay. So it's that displacement from equilibrium. A lot of times when we're talking about a physical wave, or what's sometimes known as a mechanical wave, we'll talk about displacement in terms of meters. However, there are other units. Sometimes it's more the intensity of the wave. So it doesn't necessarily have to be a distance measurement. It could be a measure of the intensity of the wave as well. Let's talk about a few other metrics for waves. The first is period. So the period is the time for one complete oscillation. All right. So if you think about waves in an ocean, and I'll use that as an example a lot initially because that's the one we're probably most familiar with. But the period would be the time in between waves crashing along the shore. All right. So how long it takes between waves, that is the period, the time for one complete oscillation. And then the frequency is the number of oscillations per second, or I always think of it as how frequently oscillations occur. All right. So period and frequency, we typically represent period with a capital T. The reason why it's a capital T is it is a time, but it's a specific time for one oscillation. And we actually saw this previously when we were talking about satellite motion. Time for one orbit was also referred to as the period, and that's a common thing. Anytime we have a repetitive motion, the time for one motion is typically called the period. And then the frequency, like I said, is how frequently oscillations occur, symbolized by a lowercase f, and is measured in hertz. That is the unit of frequency, and 1 hertz is just one oscillation per second. You may notice from this that period and frequency are similar, but kind of like flips of each other. I always think about it as period is time per oscillation, and frequency is oscillation per time. And that leads us to this equation down here, that frequency is just 1 over the period. We similarly could say that the period is 1 over the frequency. They are just inverses of each other, or reciprocals of each other. All right, our last quantity here is going to be the wavelength. And it is symbolized by this symbol here, which is the Greek letter lambda. And if you want to draw it, the simplest way to draw it is kind of like an upside down Y. So you have a line down like that, and you draw a little leg off of it. If you want to get a little fancier, you can put a little curve in your lambda and then draw your leg. But That is the Greek letter lambda, and it represents one full wave, the length of one full wave, hence the term wavelength. And when you do this, you always want to make sure you are measuring one full wave. So you can go from trough to trough, from here to here. And the key idea is that if we start here, once we get to this point, the wave begins repeating itself. So if you measure somewhere in the middle, like let's say we started our measurement here, okay, we would want to look to when this wave starts repeating itself, which would be right at that point there. And so this distance from here to here would represent the wavelength, but it's got to be one full wave cycle. All right, our last two definitions here are going to be about two different types of waves that we're going to talk about. And so for both of these, we're going to imagine a slinky here. That's going to help illustrate these waves. And so the one wave you would generate by shaking the slinky up and down, and that would create that classic wave shape that we think of, that we see with ocean waves, etc. But the other type of wave that we could generate in the slinky is by shaking it back and forth. And that would send these like pulses down the slinky, spots where the slinky is very, very close together, followed by spots where it's very, very stretched out. So let's go ahead and name these two different kinds of waves. So the first kind that we see when we're shaking our slinky back and forth and it's those pulses going down is known as a longitudinal wave. All right, and so what happens is the waving motion, the shaking motion, is parallel to the velocity of the wave. So as the wave's going down, it's oscillating back and forth like that. And I always remember it by saying that the wave pulses travel along with the wave, hence it being a longitudinal. Transverse waves, what we typically think about with waves, where the waving motion, the waves may be traveling to the right, but the waving motion is going up and down, and so you get that classic wave shape that we see before. That is known as a transverse wave. Okay, so that's typically what we think about, but we also do have longitudinal waves. Going back to our picture from before, this first wave we saw, this would be our longitudinal wave. And the second wave is going to be our transverse wave. So let's introduce our next formula here, which is how we're going to determine the velocity of the wave. And so what we're going to do to find that is if we think about some of the quantities we've already defined, wavelength is the length or the number of meters per wave. And so we see meters per wave there. Frequency is the number of waves per second. Okay. And if we multiply them together, right, just like with unit conversions, the waves part cancels out and we're left with meters per second, which is velocity. And so that leads us to this equation that we have down here. Velocity is just going to be equal to wavelength multiplied by the frequency. So if we have wavelength in meters, frequency in hertz, it will give us the velocity in meters per second. Now we're going to introduce probably the most important concept that we're going to learn this entire unit about waves, and that is this concept right here. The velocity of a wave only depends on the medium that it moves through. So this word here, medium, that just means the thing the wave is actually traveling through. If we're talking about ocean waves, this would be the water. If we're talking about like sound waves in a room, it would be the air itself. It could be a string or a slinky if we're talking about waves traveling along a string, traveling along a slinky, but the medium is the thing the waves move through. Okay? That's the only thing that affects the velocity of the wave. And you may be looking at the equation we introduced on the last slide, velocity equals wavelength times frequency, and saying, well, what happens if we increase the wavelength? Okay? That, in theory, should make the velocity travel faster, but what ends up happening is if you increase the wavelength, the frequency decreases, and vice versa. Those two have this reciprocal relationship where one will increase, the other will decrease in order to keep the velocity of the wave constant. The only way we can change how fast a wave moves is to change something about what the wave travels through. Okay, you can't change anything about the wave itself. You have to change something about what the wave is traveling through. One other quick note here that I just want to mention. Keep in mind that the medium that the wave travels through doesn't actually move. So when we have a wave traveling through a string, traveling through water, whatever, what ends up happening is if you think about like a point on a string, okay? This point right here, a wave passes through. What's going to end up happening is that point is going to rise, it might fall, but it ultimately is going to end up in the exact same spot it was in before, okay? The medium itself is not moving with the wave. The wave is kind of rippling and oscillating through the medium, but once it passes through, that medium, the substance the wave is traveling through, is left in the same position it was in before. All right, let's work through two quick practice problems here with this. So for the first one, we're told the frequency and wavelength of a wave, and we want to know what the velocity of that wave is. So we can say velocity is just wavelength times frequency. So it's going to end up being 1.3 times our frequencies here of 262. And that gives us a velocity for a sound wave of 340.6 meters per second, which is, depending on the temperature, the approximate velocity of sound through air, so about 1/4 mile per second almost. And then we want to know what could be changed specifically to alter this speed. And so the key is, as we talked about on the last slide, we have to change something about the medium. So in this case, air is the medium, so we could change the temperature of the air. We could change the density of the air, potentially if we, replaced the air in a room with helium or something like that. You know what happens with your voice, all right, when you have helium. That's really changing the velocity of the wave in that case. You could also maybe even change the humidity. Those of you that play musical instruments will know that if you tune your instrument inside on like a summer day, and then you take it outside, your instrument is no longer in tune. And that's because changing things about the air, the humidity, the temperature, etc., changes the tuning of it because it ultimately changes the velocity of the wave. For our second one, we have light waves move at a speed of 3 times 10 to the 8th meters per second, which is quite fast. We want to know what the frequency of a radio wave is that has a wavelength of 1.2 meters. That is the approximate wavelength of things in that radio wave range. And so we can say 3 times 10 to the 8th is our velocity, equals 1.2 times our frequency. So we divide by 1.2. Keep in mind, we can do that 3E8 using that EE button on our calculator. And when we do it, we get a frequency here of 2.5 times 10 to the 8th, or if you want to actually write it out, 250 million hertz is our frequency. All right, for this next problem, we have a graph here, and we want to find a number of things. We're told the velocity of this particular wave is going to be 50 meters per second, and we want to find the frequency, wavelength, amplitude, and period of this wave. So a few of these things we can just get by reading the graph. So I'm actually going to start with amplitude here. Amplitude is the distance from equilibrium to either the crest or the trough, the peak or the minimum, and so here is my equilibrium position, and so the distance from there up to this crest, or if we went from the equilibrium position down to this trough, that would be our amplitude, and so that amplitude is just going to be 6 meters in this case. We also, we want to look closely at what we have here on our x-axis, but we also can use this graph to determine one other thing, and in this case we see the x-axis is in units of meters, which means if we think about one full wave here, okay, which would be from here to here, that's where the wave begins, that's where it begins repeating itself. That distance in meters is going to be our wavelength, the length of one full wave. So we can say our wavelength is 2 meters. Now that we have that, we can do a little bit of math to get both the frequency and the period. So we can say velocity is wavelength times frequency. So 50 is going to be equal to our wavelength, which is 2, times our frequency. And so we end up getting a frequency here of 25 hertz. And now that we know that frequency, we can also calculate our period. And so in order to do that, we can say that the frequency or the period is just 1 over the frequency. Remember, we can either say period is 1 over frequency or frequency is 1 over period. They're the same equation. So I'll say that my period here is just 1 divided by 25, which means my period is 0.04 seconds. And there we have it, all the characteristics of that wave that we wanted to find. All right, moving on, we have another graph here. This time we're told the wavelength is 10 meters, so I'm going to fill that in for lambda there. And we want to go through the same exercise and find all those other quantities. I'll start with amplitude once again, measuring from the middle up to one of the peaks. And we see that that amplitude there is going to be about 5 meters. It's somewhere in between the 4 here and the 6. We'll just call it 5 meters. Split the difference. Up next, we can use our graph once again, but we notice here our x-axis is now time. All right. So when we consider one full wave, which would be from here to there, all right, that's where it starts repeating itself. That full wave is not going to be the wavelength anymore because the x-axis doesn't represent distance. All right. This is one of the weird things about waves. We can have an x-axis in terms of distance. We can also have an x-axis in terms of time, okay? Because a wave and what the displacement is depends both on the location within the medium and also the time at which you're measuring it. So the last slide we had basically a wave frozen in time, and we were looking at the displacement as a function of the position. All right. For this particular wave, we basically have one single position, and we're just thinking about how that wave oscillates through that one position. I almost think about it like being out in the ocean as waves are coming in. You'll notice the wave rises up and then it falls. And so if you think about you being in the ocean, you're going to kind of bob up and down at one location. All right. And we could track your motion, and it would look something like this. And so that's what we have here. We're thinking about how a wave oscillates through one single position as a function of time. So when we go ahead and think about one full wave here, the value on the x-axis now represents the period because it's the time for one full wave. And so from there, we can do two important calculations. Number one, we can find our frequency, which is just 1 over the period. So 1 over 2 means our frequency is 0.5 hertz. So we can fill that in. And once we know our frequency is 0.5 hertz, we can also calculate our velocity because our velocity is just wavelength times frequency. So we take our 10 meters times our frequency of 0.5 hertz, and we get a velocity here of 5 meters per second. So we can go ahead and fill that in as well.